Okay, so I think what did we talk about at the end of last class? We talked about system calls. We didn't get here. Did we get here? Did we get here?
You just kind of skipped a bunch of stuff.
Scream, scream, scream.
You skipped a bunch of stuff.
Yeah, you skipped a bunch of stuff, decided you wanted to go do it, and you went all the way back, like 4 slides, and said that's what we're going to do.
Was this it? I know we did this one. I remember this one.
We did this.
All right. So we have our. That's right.
Yeah, that's right.
So, okay, so we have our actual operating system portion of the, well, what we consider to be the operating system, either the GUI, the command line interface. This is a batch processor, which would be something that happens kind of in the background and just keeps doing things. That all filters through all the hooks that are part of the user interface, which then filter through the various system calls. So those hooks get mapped to actual system calls, which are the generic things that every operating system knows how to do. So you have the underlying kernel, and then you have the graphic user interface. So these two layers here, well, I guess you can say this is 3 layers, but you get this box up here and this line right here, system calls. This is the top layer of the kernel of the actual operating system. And everything that talks to the program execution, I/O operators, file systems, all these core operating system functions have to be done in terms of these system calls. Okay, so all these user applications that are going to sit up here, Microsoft Word, video games, whatever it is, all that stuff has to write its code in terms of these system calls. Okay, which then talk to the resources of the operating system in the way that they know how to do. All right, does that sound familiar? What's the, so yesterday in architecture, we talked about how architecture is similar to operating systems, but it's more the hardware side of things. What does this sound like from an architecture perspective? Doesn't this look like the CPU? When you write a program, that program gets compiled to a low-level language. That low-level language has to solve all the problems in terms of the system calls, in terms of the things, the magic tricks that the CPU knows how to do. And then the CPU then actually carries that stuff out. We don't know how. We don't, it has all these wires and pinouts and all this stuff that does all the magic. But at the end of the day, all the problems we solve at the low level, when your code becomes a low-level language, either through a compiler or if you wrote it yourself, they all have to be solved in terms of the magic tricks the CPU understands. That makes sense? So, exact same model, but this is on the software side. Okay, so these are the actual core underlying functions of the operating system. In the second half of the semester, we're going to be talking about each of these in detail. Okay. Talked about command line interface. I remember we were looking at that last time. We talked about the GUI thing and some of the perks of command line versus GUI and vice versa. We looked at the different shells, just briefly, just this DOS-y looking thing is the Unix shell. And you can run programs out there and it's not completely antiquated, even though most computer users today will never go out to the terminal and do anything. On a PC, there's still the command prompt, right? Is that what it's called? Still command prompt? It used to be just called the DOS prompt, and then they switched it to command prompt because now it's emulated DOS. And you could still do stuff out there. You can create directory structures and all that other good jazz. You can do more at the Unix prompt, not because Apple is magical and decided, well, we're going to make ours full functional. It's because Apple based their operating system off OpenBSD, which is a full-fledged Unix operating system. Microsoft did not. Microsoft wrote the NT kernel, so the NT kernel from day one was built more as a single-user operating system, where most people would consider, not that you can't use a Windows machine as a server, but most people would consider having a Windows machine in your desktop and having a Macintosh on your desktop as a single-user computer, right? Out of the box, the Mac would be far more capable as a server class computer. Not because the Mac is better, but because the operating system it's based on is a server class operating system. all Unix. Unix was never designed to be a single user operating system. So for those of you who are Linux users, you're taking a server class operating system that has put a pretty GUI front end on it, and allows you to use it as, what the cool kids call it, a workstation. So if you're using a server class machine for high level computer sciencey tech stuff, it's not your desktop computer, it's your workstation. Sounds cooler. So this is nothing that Apple did extra cool. What's the difference between Apple and Linux? The Mac OS X and Linux. I think we had 2 Linux users in here, right? Wall, and who else is a Linux user? Do you guys use it regularly, or just kind of hobbyist? You've installed it a couple times, messed around with it. Okay. So, what's the difference between the Mac OS, which I assume you've used the Mac OS at some point, right, and Linux? This is going to be a Mac hit.
It's graphics.
It's really graphics. What did Apple do? Apple took a not easy to use operating system like OpenBSD, and even those Linux users would you admit, I know Linux users don't like to do this, but wouldn't you admit that Windows and the Mac are easier to use operating systems than Linux? For the common folk.
Yes.
Common folk. We're going to put 100 people in front of one of these machines. We give them a fighting chance on a Windows machine or a Mac, where Linux is going to be a little bit, of a crapshoot, right? So, in any case, what did Apple do? Apple made a better graphic user interface. They called it Aqua. So they just made a better graphic user interface than Linux typically does. And that's kind of what we're dealing with today. We're dealing with technically a Unix-based operating system instead of Linux, but let's just call them the same thing. One's open source, one's not. Although OpenBSD is actually open source now. So the Linux community kind of drug the Unix community out into the open to open source some of their stuff. Personally, I like the OpenBSD daemon guy better than any of the Linux penguin stuff. You know what I'm talking. Oh, come on.
Yeah.
So we got the Linux penguin.
What's his name? Peg or something?
Tox, yeah. So there's a Linux penguin. And hopefully we don't get any of the X-rated demon ones. BSD demon. Yeah, isn't that guy like way cooler? Yeah, look at this. This is a good one. I'm not going to scroll down anymore because who knows what we're going to run into. We got a little thumbnail up here that's giving us a preview of. Yeah, Linux users tend to be a little edgy. What's up? Question mark, yeah, that's right. Yeah, when so I had this is in a former life, sort of, kind of. If any of you are interested, I can tell you the whole story. This isn't a classroom discussion, but in any case, it's not inappropriate for class. It's just kind of my backstory. About 7 years ago, I owned a yacht. Many of you are aware I've done very well for myself, and I teach because I like teaching. But if you ever want to hear the full story, I can tell it to you. But in any case, money is the root of all evil. Don't chase the almighty dollar. Do what you're passionate about and let it monetize itself. But in any case, on my yacht, I had... So I had a 45-foot cruiser. And on my yacht, I had, on the back, the name of the boat was Open Source. And I had the OpenBSD daemon, and I had the Linux penguin on the back of the boat. So... Did I what? This predated that. Yeah, I think that's only like 5 years old or something like that. That song, not even, but something like that. It's not 8 years old or 7 years old, whatever. I figure I live on Lake Michigan. You need a yacht, right? Makes perfect sense. I used to take students out on the yacht. Now we got rid of it, so we can't do that anymore. What was I talking about? Oh yeah, yachts. Don't get a boat, by the way. That was an expensive seminar. I had it for 2 years. I bought it for $500,000, and I sold it for $120,000 after owning it for 2 years. I didn't use it. I used it probably 30 times in 2 years.
Donated it to computer science.
Yes, donated it.
We actually looked at donating it to Concordia to keep out by the bluff, to take like I'm actually serious. We actually went through the process of looking at what it would look like to donate it to Concordia from a tax perspective, so that when like parents came and visited and stuff, they could take them out on the boat around the bluff and that kind of stuff.
The sad part is that's the only thing they can use it for.
It's more than I used it for. I went salmon fishing twice on it, and it wasn't made for salmon. It wasn't made for a fishing boat. It was like just made for like a, like have girls sunbathing out in the front of it, kind of cruising type of thing. But I just sunbathed on the front of it, and that didn't go over that well in at the marina in Milwaukee. Okay, so in any case, what's up? Actually, most of it was that I was blocking out the sun. All right, so really, Linux versus the Mac OS. Let's just call them the same operating system. The Mac OS just has a more user-friendly interface. And that isn't to say that the user interface on Linux is poor. But many Linux users spend most of their time out at the terminal like this. They just happen to be working in a GUI. It's not uncommon for a Linux user to have 5 or 6 terminals open at once. Where I would say it's very uncommon for a Mac user to have even 1 terminal open. It's just not the way people use those operating systems. Okay. We talked last time that system calls, operating system type things, low-level stuff is typically written in languages like C and C++. Why? Because you have direct access to memory. At the end of the day, that's what it is. It actually is kind of interesting that our modern languages have evolved let's just say evolved past the C and C++ realm. Java's completely taken memory out of the equation by running in a virtual machine, and C# has all but taken memory out of the equation by making you write anything that manipulates memory inside of an unsafe block, and then it flows through the .NET component architecture that decides how unsafe it is, and might make some changes to it or put it into protected memory or something like that so that your program can't crash other programs. On paper, that sounds great, right? From a programmer's perspective, it's like, oh, especially a beginning programmer, I can't accidentally crash my computer when I write bad code. That's a good thing. In the early days when I first started teaching, we were using the C programming language, or another language called Pascal, which was a language designed just for teaching, and then it became Microsoft Delphi, and it was a stupid thing. But in any case, it wasn't uncommon for students to write a program that literally made their machine reboot or caused them to have to reboot their machine. And you put that in context with you guys today when you're writing your Java programs, at least when you first started, you had a zillion errors all the time, right? How frustrating would that be is every single time you got the screen filled with red stuff, sometimes your machine would just lock up and you had to restart the computer because you had an infinite loop or you overwrote some bad part of memory or something like that. Wouldn't that be frustrating? Do you see how easy programming is today? It's gotten so dumbed down. A monkey could do it. Thinking about you, Abe.
Solve Evan like that.
Evan can't program.
So is he the Amish?
That's true. Yeah, Jordan can program. Evan can't. It's cool.
Wow, you're lower than the Amish.
And he works at Best Buy. All right. So in any case, these older languages are going to stick around for a while. And the irony I was pointing out is we're going to continually have operating systems, right? We're not rolling backwards where we're going to start interfacing with hardware ourselves. In fact, we're going more in the other direction, where we just keep putting more and more layers between us and the complicated stuff. Isn't that true? Every new piece of technology comes out is easier and easier to use. Even we take it out of, the standard computers, the big talk this year with automotive is self-driving cars. Let's fast forward 10, 20 years. It might be uncommon for somebody to know how to drive a car. You just get in and turn a key or push a button or put your thumbprint on it, whatever. So now we won't have this idea of driver's license. You'll have 8-year-olds taking the car to the playground. Yeah, this is the direction we're. So everything's moving farther and farther away from us doing things ourselves, right? We've already seen it with shopping. How many of you prefer to shop online rather than actually go to the store? Heck, I buy milk online. There's this dude, he drives this big truck called Peapod. He just comes to my door with milk. And there's no minimum order. If you're out of milk, you can just order milk. Yeah, they'll just bring it. You can go on to Amazon. You can order lobster. That was on a Big Bang Theory episode, and it's true. No, and you can get live lobster off Amazon. They ship you an animal. I don't think it does.
$143 for 2 lobsters.
Oh, those are live ones?
Live, yeah.
No, that's very expensive. But you can do it without putting pants on. That's right.
Approximately 2 lobsters.
Yeah. What does that mean? They're live. What does that mean, approximately 2 lobsters?
One of them's tomatoes cut up.
There's like 5.
One of the rubber bands comes off and they've just been pecking at each other.
Live is in quotes.
What does that mean?
You may not be
10
lying.
pounds of live
4 to 6 pounds.
New England lobsters. So
4 to 6 pounds. Actually, those are big lobsters. That might be worth $140. What kind of monster when they're selling? When they're shipping you some of like some kind of World of Warcraft boss in a box. Yeah, the current rage. You got this giant lobster-looking guy made of. He's a robot. That's somebody we fight. Doesn't make any sense. Who built that guy? I always think it's funny in those video games when you get to boss fights and 25 people are staging over in a corner and the dude's just kind of standing there waiting for you to attack. And why is this guy standing in a room by himself? Doesn't make any sense. Doesn't he have something better to do than just chill over in a corner waiting for people to attack him? See, that's why we have programs that play video games for us. So that we don't have to waste our time with that. That's right. Lobster fights.
live.
Okay. So in any case, we need these older languages in order to do some of the stuff, and we're certainly not rolling backwards. So that kind of makes an argument that C++ is likely not going anywhere. We really can't look at Java and C# and say those are better than C++. They are different tools. Using Java or C# for writing application programs probably makes a lot of sense. Java, if you want to make it cross-platform and it has less of a requirement for speed. And C# if you're writing it for Windows and you want it to be fast. But C++ is still going to be required for writing our operating system stuff. And C probably isn't going anywhere anytime soon because some of the older libraries are written in C. If you've ever taken a look at the open source Linux kernel, there's tons and tons and tons of it that's still written in C because it's just been drug along from Unix from 20 years ago. We've updated all sorts of crap around it, but there's some there's some parts that are still the original parts. So kind of an interesting thing on the evolution of languages, I guess. Okay, this is a stupid slide.
How come you don't teach a C++ or C faster?
Well, in some cases I do when I talk about pointers and stuff like that in the other language, in like Java or something, we typically look at some C and C++ code. I'm not sure beyond that how advantageous having an entire class on C++ would be, because it's really the same as Java minus pointers. And the languages are very similar. So I wouldn't think there's a huge jump. We do teach the iPhone classes, which use Objective-C, which are very similar. I mean, those heavily use memory. You can't create a variable that isn't a pointer in Objective-C, which is actually kind of interesting. We say pointers don't exist in Java. It's because in Java, everything's a pointer. Well, really, it's just as true to say pointers don't exist in Objective-C, because they force you to make everything a pointer. So why do they even have the syntax for the asterisk? In Objective-C, the Apple, iPhone, Macintosh programming language, whenever you create a variable, you always have to put an asterisk after it saying it's a pointer. Java, you don't put an asterisk after it saying it's a pointer. Just very funny. Not primitives. Yeah, not primitive types, but like NS array, pointer, blah. Yeah. So I guess, Abe, the official answer to your question would be, you already know a large portion of C++. See, now you can put it on your resume. That's what it's all about, right? Putting fluff on the resume and hope you don't get called on it. I'm doing a job interview for a guy for my company this afternoon, and I'm going to give him a programming test. He's got in his resume like all this programming experience, and I'm like half expecting him to not be able to write "Hello World." It's going to be funny. Dave can write "Hello World." Dave just doesn't pay a lot of attention to detail when he's on the spot. Those are two very different things. Dave's my pet project for 4 years. What was it talking about?
Well, I think this is a new slide.
Is it? Is this a waste of time? This is a wasted slide. Let's call that a wasted slide. Oh, this is only sort of a wasted slide. So this would be like an example of a system call. So we might have a program called readfile.c. So that would be a C program that somebody wrote at some point. You have to pass it some inputs. So command line. So in Java, we hardly ever use them, the string array args. But C programs often use those. And I think I showed that, last time. And pretty much everything you do takes command line arguments. If this is a program called ls. If I only want to look at things that start with an H, I have to give it a command line argument for the filter. And it only gives me the H stuff. That type of stuff. So somewhere there's a program called ls.c. When it's compiled, it would compile to a.out, which is then renamed to ls. And that's the actual binary executable. So if you went and looked at the source code for the Mac operating system, somewhere there would be a program, a file called ls.c that when compiled produces this program. This program is no different than like Microsoft Word, except it is far smaller and does far less. It still does something important. Okay, so these would be command line arguments. So we have to say, I want to read this file. Passing, this is going to be a character, more than likely a character pointer. It's a void pointer. Buffer to read into. So we're going to read a file from the hard drive into something in memory. So that's the way that a file goes from hard drive to memory, is through something like this kind of system call. How many bytes are we going to read? How many bytes were actually read? I have no idea what this one is.
It says in the bottom.
Oh, does it? I still don't know what that means. Indicates if overlapped I/O is being used. Oh, I suppose maybe that is multiple calls, so maybe it's a slowdown. Because you might have to call this multiple times in order to read enough bytes to get the whole file. Chances are you don't read the file into memory all at once. You might have a 1 gigabyte file. That's a pretty massive text file, but let's just say it's a 1 gigabyte text file, and we're going to read that into memory. Well, that's going to load into memory very slowly. So chances are, if it's a text file, you're only going to be looking at so much of it at once. So if you've ever opened up a Word document, it's a really big document, and you start trying to scroll through it really quick, it starts getting choppy, right? Because it has to pause while it's loading more of it into memory. Okay. So that would be an example of a system call. So whoever's writing Microsoft Word, for example, if you go to File and Open through that application program, underneath the hood, it's going to have some high-level language for opening a file. You probably create, let's just assume it's in Java, since that's what most of you are familiar with. Somewhere it's going to open up a print stream to a file to read it in, and then when you compile it, that's going to turn into Java bytecode. At runtime, the Java virtual machine is going to interpret that Java bytecode into an actual low-level language that executes on the CPU, which is ultimately going to call the read file function to actually read the file. Make sense? So there's a whole bunch of little switches that it went through till it finally got down to what it's actually doing. What is that? Is that a beeper?
Why do you wear it?
It's low battery. Is that for campus here?
Yeah, for my job at AB, I'm the on-call person, but it's during work hours, so I don't know why it would ever go off.
Huh.
Why do you have it?
Man, who uses a pager? I didn't even think I know in network administration, it's actually somewhat common for people to still carry pagers because you can set up programs that will page you like when a certain service is down or something like that. So you kind of get notified of it prior to something else. But with the advent of push notifications on your smartphones, if everybody's carrying a smartphone, I'm not sure why pagers still exist.
There's those people who are just like, I can't afford a smartphone. I don't want one.
Chances are, if you're in IT and you're a server manager person, you're gonna have a smartphone.
Computer science has their blasphemers
Yeah,
too.
but push notifications could be anything. If you have a pager, you set that up to only be paged when something's
Yeah, but what if you're in like a public place and somebody just slaps you because you have a pager? It's like, boom, you stay down.
If someone had a pager, would you do that?
I'm almost tempted to do it now. Yeah, it's recording. It's the weird one where it's on a certain screen. The program's just funny. What was I talking about? I remember back in the designer pager days. You go into places, they have like pink pagers and like pager cases. That was when pagers were cool. Then they came out with flip phones. Well, no, then they came out with bag phones. No, pagers came after bag phones. Then they came out with flip phones, and those were cool. Like Motorola Razr. I had the time port. Twice the price, half the features. Okay. Wasted slide. We pretty much already said this, right? Just another picture for the same crap. Okay, well, there already exists a standard C library. So if you're writing your applications, like we just mentioned a few minutes ago, we would have a program called like ls.c or something like that. If you're writing those, there's already standard C functions for making those system calls. You can actually make system calls directly if you want, or through the standard template library, something called STL. It's kind of a make C++ more like Java type library. There are some tools that allow you to make multiple system calls through a single high-level call. But that's built into the C programming language, these standard things. And why is that? C was originally designed for writing operating systems. That was the point of C. And then we just applied it to other things. So kind of an interesting thing there. All right, system call parameter passing. Often more information is required than simply identifying a desired system call. Exact type and amount of information vary according to OS. 3 general methods used to pass parameters in the operating system. Pass the parameters in registers. So, for example, if you have a system call and you happen to know that that system call is going to hit 2 or 3 different registers to get its information, what you would do is you would load your parameter information into those registers, then make the system call, knowing the system call is going to go and read from those registers. So that's one way it might get its parameters. Okay, if you're using a built-in function that's built into something like C, well, chances are you're going to make C's system call, which is going to load the registers for you, which then makes the real system call. Kind of make sense? Because as programmers, we don't like operating at that low of a level. You know, when you're writing your Java programs, you can appreciate the fact that your CPU has hardware registers on it, hardware-based variables, but we don't necessarily operate at the level where we care what's in them. We just know that something good is in them that's getting used correctly, right? Well, so this is one way that a system call could receive its parameters, is through hardware registers. Parameters could be stored in a block or a table in memory, so a specific location in memory. An address block passed as a parameter in a register. So we might store the crap up in memory somewhere. So let's just assume it's an array that contains 50 things that system call is going to need for whatever reason. Maybe we're deleting a directory of files. So we're going to put 50 things up in memory inside of an array. Then we're going to store the pointer, the address of that memory location in a register. Then you'll call the system call, which will read the address and then go up into real memory and do what it's supposed to do. So again, it's using register, but it's using registers as a middleman rather than actually storing the real value in the register. So this would be a hardware-based pointer. That one. Parameters could be placed or pushed onto the stack by the program and popped off the stack by the operating system. So many of you have already had the 300 class. What's a stack? If you haven't had a 300 class and I say you have a stack of magazines, tell me what a stack is. Collection of items piled on top of each other, right? And when we put stuff onto a stack, where do we put it? Top of the stack. You know, if you have a stack of cards or a stack of magazines, chances are you're not going to take the next card or the next magazine and shove it somewhere in the middle. We're going to pop it on top of we're going to push it on top of the stack if we're using the computer science terms. When we remove something from the stack, we typically take it off the top. So we're going to pop it off the stack. Most modern operating systems, and we can go significantly far back and still this is a true statement. So most operating systems have a built-in stack data structure that's available to everything across the operating system. So think of it like memory, but it's kind of organized memory. So that stack's going to live in real memory, so we kind of have this resource that's in memory that we can throw things at, and it gets put on top of that stack. So another place that we can put our parameters for a system call, if that system call worked this way, if it was stack aware and it knew it was going to get its information from the stack, we might throw out those parameters onto the stack and then make the system call, knowing the system call is going to go and look at the stack. So what's interesting about the block and the stack methods, so either storing stuff directly in memory or storing parameters in the stack, which ultimately is being stored in memory. This is just another middleman. What's interesting about that is we're not limited to the amount of information we can pass to a system call. You know, if you're going to store stuff directly in registers, I guess we have a finite amount of memory too, but you have a very finite number of registers. Finite number of places you can put parameters in the hardware registers. So if you're doing that, you're probably dealing with a system call that requires 1, 2, maybe 3 pieces of information. If it requires more than that, it's going to make a lot more sense for us to put it up in memory or put it someplace else and store 1 pointer in a register. That make sense? Do we even need the pointer in the register if we use the stack? Probably not, because the stack is something owned by the operating system, so everybody's aware of it. So rather than going to the hardware register, then going up into memory, the system call can just go right to the stack. That make sense? So, 3 different ways of kind of accomplishing the same things, but you have some flexibility using memory or using the stack. So the question might be, why don't we always use the stack? Or why don't we always use memory? Why would you ever create, why would somebody did this originally? Why would anybody ever create a system call or leave that system call in place by today's standards that gets its parameters from a register? Speed. Yeah, it goes back to talking about the speed of those different things. So it's all about the speed of it. If you need a system call that's reliant on being fast, the faster you can get its inputs, the better. So parameter passing via table, we just kind of talked about that, where you use this guy as a pointer up into memory. So we said that already. Types of system calls. So we have a type of system calls dealing with processes and dealing with files, for instance. So we can end or abort a process, load or execute a process, create processes, terminate processes, get the attributes associated with a process, set process attributes. We can wait for a period of time, wait for a certain event, signal an event. So this kind of goes into when we talked at the high level about inter-process communication. You might have two threads or two forked children. Okay, so you have two child processes, and one of them might be responsible for doing something, and the other one might be responsible for something else that's reliant on this guy. So one of the children might wait for a system call that comes from this guy, a signal that comes from this guy. So those are things that processes can do. They can make system calls that raise awareness to other processes, something like that. We can allocate and free memory. Under file management, kind of makes sense. Create files, delete files, open and close files, read, write, and reposition files. Get, set file attributes. So things like whether or not the file is read, write, execute, who has permissions to it, that kind of stuff. For device management, we can request access to a device, we can release a device. This is actually also an example of inter-process communication. Typically we accomplish this through something called a semaphore. We'll talk about that, but it's a control block. It's just an integer that controls access to a specific resource. So if we're accessing something where there's only one exists, we're going to request that device, and we'll be blocked until it's our turn. And when it's our turn, we have exclusive access to that device, and when we're done, we're responsible for releasing the device. That makes sense? So kind of an interesting thing, depending on what protections. If we go back to older operating systems, if you were to write a virus, what you could do is you could request a device and never release it. So let's use something like I think we use printers less today than we ever did, probably because we're always emailing documents and things like that, but we still rely on printers to a certain extent. But let's go back to a little bit the earlier days where printers were used heavily. Well, chances are there's going to be less security around your printer than there's going to be around your CPU. So you could write a little program that runs on the machine that requests the printer and then never releases it. In older operating systems where maybe only one print job could go to the printer at a time, now printers themselves have memory built into them, right? You can send 30 print jobs to it, and it stores the print jobs in the printer, and then the printer just deals with them in order. But in the earlier days, all that logic was on the computer side. Well, what if you wrote a program that requested the printer, did nothing with it, and just never released it? Nobody else can use the printer now. Does that make sense? Interesting thing with devices. Read, write, reposition. So read from a device, write to a device. Get the device attributes, set the device attributes, logically attach or detach devices. So notice that we're using this generic term device, and we think about all the different kinds of devices we hook to our computers. We hook mice and keyboards and jump drives and external hard drives and scanners and printers, and we can just keep going with that, right? All sorts of different devices. The device drivers, pieces of software that teach your computer how to work with them, are all implemented in terms of a subset of system calls that know how to talk to generic devices. Does that make sense? So it becomes a very interesting, I mean, what we're hopefully seeing here is that there's a lot of levels of complexity between what we're used to using on our operating systems and what actually happens at the low level. When we click something in one of our application programs like Word, that doesn't instantly just happen at the hardware level. There's 2 or 3 or even more layers of software that request goes through until it finally turns into a bunch of little simplified system calls. Okay, so really, it's quite impressive how stable operating systems are today when you have that many things going on at once and that much stuff that has to happen with each one of those things. Very interesting. Information maintenance, get time and date, set time and date, get system data, set system data, get and set process, file, or device attributes. Communication, we can create, delete communication connections. Well, by today's standards, communication connections can mean a lot of different things, right? So we think about the evolution of operating systems. Back before the idea of networking even existed, communication would have probably happened just between processes on the computer. Now we can have communication that exists between devices. You know, that happened probably pretty quick. Then we had communication that happened between maybe computers on a local network. And now we have communication that happens across the entire internet, right? So over the years, the communication system calls have had to expand to be able to support new types of communications. So there was a point in time, and we got to go back to the history of operating systems. We had Windows 3.1 and we had Windows 3.11 for workgroups. The big addition there was support for networks, network communication. So chances are, probably amongst other things, some new system calls were added that supported communication over a network, allowed you to make communication channels outside of that physical computer. So kind of an interesting thing there. Send and receive messages over those communication connections. Transfer status information, attach and detach remote devices, which would have never existed before we had network stuff, right? Okay, so some examples of Windows and Unix system calls. So Windows, to create a process, we just call create. And Abe, would you? In Unix, to create a process, we call fork. To exit a process in Windows, an exit process, just exit in Unix. Wait for single object, wait. File manipulation. Create file, read file, write file, close handle, open, read, write, close. Doesn't the Unix ones look very simple? There's no who? There's no reap. That's the exit. Yeah, we could write a little program that just calls exit. We call that program reap. One line. Whatever you pass to me, call exit. So this is actually kind of interesting. If we look back at older system calls, so these were programs written back in the 60s or 70s probably, notice that function calls tended to be what we can call these function calls, but really they were actually calls to programs. But function calls were lowercase, typically very short. Whereas modernly, we get very verbose with them, where you can read what each of these does. So if you didn't already know what forking meant, Abe, create process makes a lot more sense, correct? You know, we know what that does. What does it do? It creates a process. If we just showed somebody the word fork, they might think it's an eating utensil, maybe a misspelling. All right. So some examples of modern system calls. The Unix ones would be applicable to the Mac side of things, since Apple had just stole OpenBSD and put a pretty front end on it. So these guys would be what the Macintosh ones are. So whenever somebody brags that Macs are really, really good, just say, you can thank Unix. Something like that. I mean, I agree. I really like the Macintosh operating system, but part of it is that I can get down to the Unix side of things and do a lot of crap with it.
It's without the drawbacks of having to worry about multiple hardware issues.
Well, true, but that's because of device drivers, which is what you're saying.
Yeah.
Is, because the Macintosh operating system is more accepted than Linux, there are more device drivers for Mac than there are for Linux. So you can use a wider array of device drivers. And then we can take that one level further and say Windows has far more users than Macintosh, so there's even more device drivers for Windows than there are for Macintosh. Macintosh, Apple writes all the device drivers, or at least certifies them. So if you have a Mac, even a Mac Pro, that is the most upgradable Mac. Other Macs, you're pretty much stuck with what they have, minus memory and hard drives. But if you have a Mac Pro, which is upgradable, and you want to get the latest, greatest graphics card, you might not be able to. There's only a set of a couple of graphics cards that the Mac even supports. Not because it won't physically fit in the computer at the hardware level, but because the computer doesn't have the necessary device drivers to run it at an optimal level. It'll just show VGA support, the basic support for it. Whereas if you have a PC and that you've built or whatever, and NVIDIA or ATI comes out with the latest, greatest graphics card, you know right off the bat that in that box is going to be a DVD with the driver for that guy, or at the very least, you go out to NVIDIA or ATI's website and grab the latest driver for it, and Windows will run it just fine, right? You actually, just kind of an interesting thing to finish up, you can actually run into some issues if you have a Macintosh computer that you're dual booting. So this would only really come into play for a Mac Pro. But if you have a Mac Pro and you go out and get the latest, greatest graphics card, you may even have issues getting that graphics card to run on the Windows side, depending on the version of the hardware and whether or not the Apple motherboard allows certain communication to happen between that graphics card and the motherboard. So just because you have a machine that you can put the latest graphics card in and you can run Windows on the machine doesn't necessarily mean that you'll be able to use that graphics card. So kind of an interesting thing if you're a gamer and interested in maybe spending a bunch of money to get a Mac Pro, don't necessarily assume you can put any graphics card in there you want. So if you're a gamer and you're building a machine, build a PC. It's the punchline. All right, I will see everybody on Friday. Yeah, we're gonna have our midterm next week. We'll talk about it on Friday which day. It's either going to be Wednesday or Friday next week, one of the two. I'll decide, but we'll definitely talk about it. I'll put some sort of study sheet up, or at least we'll talk about here's the crap you should know, and you'll have an opportunity to look over that and come with questions in the following class. All right, we'll talk more about that on Friday.